Good morning, JSConf. So you already know my name. I've never seen it this big. Can someone take a picture of it for me? I'll be grateful. OK, today I'd like to share with you some of the questions I was asking myself about numbers in JavaScript. Because even Brandon Ike yesterday at his keynote told us that the numbers are not really perfect currently. That's why all these new types of numbers are being introduced for future versions. But today I'd like to focus on what currently we have in JavaScript in terms of numbers, because if you ever tried to do some computations on decimal fractions or large integers in JavaScript, you probably have noticed that they are not really precise and may lead to some quite unexpected results. Let me give you some examples of that. If we try to add 0.1 to 0.2, you would expect it will be equal to 0.3, but it's not. What it's actually equal to is a number very close to 0.3. On the other hand, if you take quite a large integer, like, for example, this one, and you try to add 1 to it, you will get exactly the same number. But if you add 2 to it, you get the result as expected. But it's not only about inaccurate results of some computations. There are many different weird things about the numbers in JavaScript, like this infamous not a number value. So not a number is a value you will get if you try to turn into a number something that is not a number. So let's try something like this. But if you try to check the type of not a number, it will tell you it's a number. And every time I stumbled upon something like this happening I was asking myself, why does it happen? Because there has to be a reason, right? Things like that don't happen without the reason, at least in most cases. And if you're asking yourself a question about JavaScript, there is one sure place to look for the answer, the ECMAScript standard. But all the standard says about the numbers is that they are represented by the double precision 64-bit format IEEE 754 binary floating-point arithmetics. Actually, yeah, it says a little bit more than that, but nothing about how the numbers are represented in the memory, how the calculations are done. So I had to look further, but it turns out that JavaScript is not the first language that uses this standard. There are many others. If you try, for example, Python, we have exactly the same problems in here. Something more modern, like Ruby. Nope. And, of course, Java. Actually, I had to write a class to add these two numbers in Java. But, yeah. Anyway, it turns out that we have these kind of numbers in JavaScript because they were in Java at the first place, right? So I was still asking myself, why does it happen? What is wrong with this representation of the numbers that we have such imprecise results? And the first step I wanted to make was to see how a given number looks like in this binary representation. I wanted to see every single bit of this 64-bit representation. Unfortunately, in JavaScript, we don't really have easy, direct access to bits in memory. But with a little help from my friends, typed RIs, I was able to create myself a little utility function. So now we can turn any number, let's say our 0.3, and see how it looks in its binary representation. So these are all 64 bits of binary representation of number 0.3 in this double precision floating point. So let's compare it to result of the computation of 0.1 plus 0.2. It's almost the same, but if you look at the last 3 bits on the right side, you will see that there is a little difference there. And yeah, we can take any number we want, like, I don't know, 2013-09, and see how it looks like. But looking at these zeros and ones doesn't really give us any kind of understanding what is going on there, how these numbers are computed. Fortunately, because this standard is used in many languages, there are quite a few resources online that tell us how does the standard work. I gathered a couple of these here. But unfortunately, they are full of crazy equations and operations on binary numbers, and it took me quite a few long evenings, a lot of paper, to get my head around how it really works. So here I am to save you the trouble, and hopefully after this talk you will actually be able to understand this Wikipedia page. So let's see how this representation works. So as I've already mentioned a couple of times, we have 64 bits to represent our number, and they can be divided into 3 parts. There is 1 bit for a sign. It's this guy in here. It tells us if the number is positive or negative. There is this big chunk on the right, 52 bits. Actually, it's 53 because one of them is hidden. I will talk about this guy later. This part is called significant. If you are American English user, you probably call it mantissa. Sometimes it's referred as a fraction. But basically, these 52 bits are representing the binary digits of our number. And some of them are used to represent the integer part of our number, and the others are for the fraction. And I use this point in here to show where this split happens. So these bits on the left of this point are used to represent the integer part, and the rest is for the fraction. And the remaining 11 bits is the exponent. And the exponent is kind of a multiplier that is used to scale the value given by the significand to give us the final value of our number. And I'm pretty sure it's quite confusing at this point. So let me give you a little bit of analogy. I hope that you've, at least at some point of your life, seen a number written like this. It's so-called exponential or scientific notation. So in this notation, we also have a number divided into 2 parts. There is this part. It represents the significant digits of our number, so all the digits we want to have in our number. And it's also called significant. And we compute the number by multiplying it times 10 to the power of the exponent. So the exponent is kind of a scaling factor. So the bigger the exponent gets, the bigger our number will be. And the smaller the exponent gets, the smaller value of our number we will have. And we can look at this exponent as kind of defining the position of the point in our representation, because when the exponent gets higher, the point kind of moves to the right and makes this number bigger. And when the exponent gets smaller, it kind of moves the point to the left, making the number smaller and smaller. And actually, the roles of significant and exponent in this binary notation for the floating point numbers are exactly the same. So let's get back to it and see how it works in more details. So the sign bit, there is not much to say about this guy. If its value is 0, the number is positive because it's counted as the power of -1. And if we turn it to 1, our number becomes negative. Simple as that. Exponent is a little bit more interesting. So we have 11 bits to represent the exponent, and the exponent is an integer value, so we can represent the number from 0 to 2047. But we would actually want exponent to have negative and positive values. So what is actually used is so-called offset binary notation. So we take the number computed from the powers of 2 from the bits of exponent, this one, and we subtract 1023 from it. It's exactly the half of the range. So when our value computed from the exponent bits gets exactly to this point of 1023, our exponent will be 0. And when it gets lower, the exponent will be negative. When it's higher, the exponent will be positive. And this number, the value for the exponent, is actually defining the position of this point in the significand. So it defines how many bits we have for the integer part of the number and how many are left for the fraction part. So the bigger our exponent gets, the more bits we have for the integer part, and the bigger our integer value gets, the smaller exponent is, the point will move to the left, giving us less bits for the integer part. And actually, that's why it's called the floating point, because the position of the point depends on the value of the exponent. So now, let's have a look at the most important part, the significand. As I told you already, we have 52 bits. These are these red ones. And here, this first guy is this hidden bit. We can see him here. Yeah. And we can see him because we don't actually control its value. Its value is always assumed to be 1. So that's why we don't have to put them into 64 bits, because we can't change it to 0. So to explain you how this significand works, let's start with something simple like number 1. So for number 1, our exponent is 0, so it puts our point in here. So we have 1 bit on the left-hand side, this 1 bit, representing our integer part. And it represents 2 to the power of 0, so it's 1. But we have only 1 bit for the integer. We can't represent any bigger number. So if we try to represent the number 2, we have to move the point to the right by changing the exponent. So now we have 2 bits for the integer part. This first bit is representing 2 to the power of 1 at this point, so it gives us 2. And the other one is representing 2 to the power of 0. So we can represent also number 3. But again, we just used our 2 bits in the integer part. So to represent number 4, we have to again move the point to the right by changing the exponent. So now we have, oops, sorry. Yeah, I was at 4, I guess. So now we have 3 bits for the integer part. The first one represents 2 to the power of 2. The last one represents 2 to the power of 0. So the bigger number we want to represent in terms of the integer value, the more bits we will need for the integer part. Now, let's see how the fraction part works. The first bit after the point represents 2 to the power of minus 1. So it gives us 1 divided by 2 to the power of 1, so it gives us a half. So by changing this first bit after the point, we can represent 0.5 fraction. The next one is representing 2 to the power of minus 2, so it gives us a quarter. Next one is 2 to the power of minus 3, it's 1/8, and so on and so on. Every single bit in the fraction part represents smaller and smaller fraction based on the inversed power of 2. So what it tells us is that we can only build the fraction of our number by adding up these inverted powers of 2. And unfortunately, not all of decimal fractions can be represented this way. So if we take our 0.1 example, we can see that to form 0.1, we are adding smaller and smaller powers of 2. But actually, they will never add up to exactly 0.1 value. So this value is already stored in this representation with a little bit of error. And these errors add up when we do some computations on these numbers, and at some point they show up. So the limit of this representation in terms of accuracy of the fractions is based on 2 factors. First factor is that we are building our fraction from the inverse powers of 2. And the other factor is that we actually have quite limited 52 bits of significand. We can't represent the smaller values. What is even more important is that the bigger number we get in terms of the integer value, so when we need more and more bits for the integer part, the less bits we have left for the fraction part. So when we move the point right to the end of this representation, let's see to this point, for such a large integer's value, we have only 1 bit left for the fraction part. So we can only represent the half. We can't represent any other fraction for such a large numbers. So what happens if we move the point even more to the right? If the exponent is equal to 52, we have all the bits of the significand used for the integer value. There is no bit left for the fraction part. So from this point, we can only represent integer's value. So the biggest integer value that actually fits into this significand is this one. We've used all the bits in the significant part to represent this number. Now, what would happen if we try to represent the bigger number? Let's see. Let's change that. What happens is kind of what we expected. We moved the point to the right to make more space for the integer part. So we have right now 53 bits for the integer part, but actually there is no bit left there. So how the number is computed? So what happens is that it's assumed that all these bits that are missing are zeros. So this number is actually accurately represented because this last bit is assumed to be 0. But what would happen if we try to add 1 to it again? We can't, because we can't change the value of this last bit, because we don't control it. It's always 0. So the last bit we actually control is this one, and it represents 2 to the power of 1. So we can only add 2 to this number. So from this point, when the exponent is equal to 53, we can only represent every second integer until we get to this point. And again, to represent the bigger number, we again have to add 2 to it. We will move point to the right. So right now we have 2 bits that are assumed to be 0. So the last value, the last bit we control, is representing 2 to the power of 2. So it's 4. So we can represent only every 4th integer for exponent equal to 54. So the bigger the exponent gets, the bigger gaps we will have between the integers values we can represent. So actually, starting from this exponent 52, we already have gaps between the numbers, so actually any operations on such a large integers will have some error. And similar thing happens on the other side of the significand. If we make it smaller, or maybe not that small. When we have the exponent value of -1, so our point is right before the hidden bit, this hidden bit represents a half, and every other bit in the significand represents smaller and smaller powers of 2. And when we move the point to the left, we are getting some missing bits assumed to be zeros. Our first bit in significand represents smaller and smaller power of 2. So we are getting closer and closer to 0. But when we have this bit, the hidden bit assumed to be 1, it always represents some power of 2. It can be very small, but there will be always some value in here, right? So we will never be able to represent number 0, because we will always have some value given by this bit. Fortunately, this representation has an exception for that. So when our exponent gets his lowest possible value, so when all bits of the exponent are 0, so our exponent is -1023, the hidden bits also turns to 0. So this way, we can represent 0 as all the bits being 0. And we can, of course, change some bits in the significand to represent numbers very close to 0. They are called subnormal values because of this hidden bit being 0. But you may remember this sign guy in here. And I told you that we can use it to change the sign of any number represented in this representation. So what would happen if we change the sign of 0? Yeah, we will get -0. Actually, the floating point representation defines two zeros, positive and negative one. In JavaScript, it's not very easy to notice this -0 because there are only certain operations that return it, like dividing by -infinity. But it's there, and the difference between -0 and +0 can be actually detected. So we've seen what happens when the exponent is, when the exponent is at its lowest value. So now let's see the other side of the extreme. When we have all the bits of the exponent set to 1 for the highest exponent value, this is the value reserved for the infinity. Positive or negative infinity. So that's how the infinity looks like. All the exponent bits set to 1 and all the significant bits set to 0. And what will happen if we try to change the significant bits to 1? Bang! We get a none. And it's not because there is some error. Actually, floating point representation defines not a number value. So if all the exponent bits are set to 1 and any bit in the significand is set to 1, it's not a number value. So it kind of explains why not a number type is a number, because not a number is a value defined by the floating point representation. It's defined by 64 bits like any other number. Actually, we have 52 bits in significance, so there are quite many not a number values defined in this representation. Fortunately to us, JavaScript simplifies it to only one, not a number. Yeah, but let's get maybe back to numbers and summarize it what we already heard here. So, for any given number, we can compute its value by computing the values of the significant bits with the position of the point based on the value from the exponent and the sign defining the sign of our number. But as I told you at the very beginning, we can treat the exponent as kind of a multiplier. So if we take it out of this parenthesis and treat it as a multiplier, we start to compute the significant value always starting with 2 to the power of 0. It's the value given by this hidden bit. So we can always set it to 1 because 2 to the power of 0 is 1. So that's the one given by the hidden bit. And here we have the value computed for the exponent. And this way, we kind of reversed engineered the equation for how the numbers are computed in double floating point representation. And that's the equation you can find in similar fashion on this Wikipedia page. So I know it was quite a hardcore topic for a Sunday morning after the great party, but I hope that I have given you at least a little bit of understanding how numbers in JavaScript work and why we have all these problems with them. And hopefully after this talk we can all think about ourselves as those who understand binary. And maybe next time you stumble upon some weird behavior with numbers or with JavaScript, you will ask yourself why, because answers and reasons are out there waiting for us to find them. So be curious, because there is hell a lot of interesting things you can learn and sometimes quite unexpected answers you can get. So that was all I had for you. You can follow me on Twitter.
Do we have any questions? Is there anything left that you didn't want to know about numbers that you somehow want to know now? Yes. Sorry, can you keep your hand up? Oh, there we go, sorry. My tracking's not so good.
Hi, I'm Yves from SoundCloud. Thanks for the talk, it was great. I just want to add something. If you want to work with big numbers, you can actually use libraries for that, which are called big num libraries. These exist in most languages, and yeah, I found myself in this situation, and yeah. Thanks.
Yeah, that's true. I was just focusing on the numbers representation, how they are in this floating point.
All right. Okay, thank you so much, Bartek.
Yeah, thanks.